Bringing damage to your burrow. We some brothers from the east with them beats that be thorough. Got the solar gravitation, so I'm bound to pull it. I gets down like brothers of.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now let's move on to do some example problems for the photoelectric effect. So the following questions relate to the same metal used in a series of photoelectric experiments. So for the first one, it asks if 3.61 times 10 to the power of negative 19 joules is required to remove an electron with zero kinetic energy from a metal surface, what would be the longest wavelength light that could do this? So I put this picture for you right here to remind you of the photoelectric effect. And so the energy required to remove an electron is given, and it's asking what the longest wavelength of light that can be shone to do that. And so combining the two equations, E equals h nu, as well as another equation that I mentioned before, C equals lambda frequency. This is the speed of light equation, which is the product of the wavelength and the frequency. This gives E equals hc over lambda. H is Planck's constant, c is the speed of light, and this is the wavelength. Okay, so from here we can figure out what the wavelength is by rearranging the equation, hc over E. So plugging in the values, we have 6.626 times 10 to the power of negative 34 joule second, multiplied by the speed of light, 3 times 10 to the power of 8 meters per second, divided by the energy value that was already given to us, 3.61 times 10 to the power of negative 19 joules. Make sure that all the units cancel out, and you end up with meters, right? And the answer is 551 times 10 to the power of negative 9 meters, which can also be written as 551 nanometers. So that's your answer. So basically, by using these two equations that are very important, we rearranged it to create a very important equation in itself, E equals hc over lambda. This is very useful, so I suggest that you guys remember this. Okay, so in another experiment, a shorter wavelength light source is used, resulting in ejected electrons with a kinetic energy of 4.2 times 10 to the power of negative 19 joules. So this is the kinetic energy of the electrons that are being ejected. What is the energy of this incident light? So basically, what's the energy of the light that was shone in? And what's the wavelength of that light? Okay, so previously we talked about the energy of a photon. Can be written as the threshold energy plus the kinetic energy. So the threshold energy is 3.61 times 10 to the power of negative 19 joules. The reason we can get this is because before, in the previous problem, they said that this is the amount of energy required to remove an electron with zero kinetic energy. So this zero kinetic energy gives us the clue that this is the threshold energy. And also, since I mentioned that the same metal was used in a series of photoelectric experiments, this threshold energy is going to remain constant because that is different depending on the different metal that you used. Okay, so from here, we also know what the kinetic energy is, 4.2 times 10 to the power of negative 19 joules, which is this value right here. And we end up with a sum of 7.81 times 10 to the power of negative 19 joules. So from here, what do? We use the same equation again, but this time we want to solve for the wavelength, right? Because this was the answer to part 1, which is here. So now for the wavelength of this incident light, we can plug in the values that we have, where h is again a constant, 6.626 times 10 to the power of negative 34 joules second. C is a constant, 3 times 10 to the power of 8 meters per second, and we just calculated the energy of the incident light by using this equation. And so that was 7.81 times 10 to the power of negative 19 joules. So let's check that everything cancels out, and we end up with a value of 255 nanometers. So in these two problems, we were able to calculate the energy of the incoming incident light, also the wavelength of that light. And as you can see from here, if someone asked you to calculate the frequency or the energy, you just basically rearrange these equations to solve for it.
This is high. You know the stakes is high when you're dealing with the